Now, on part 2 of calculus with parametric curves, we're going to actually see in place the use of the formula for area, for arc length, and for surface area. So let's go to one first example. We want to find the area under the curve of one arc of the cycloid. The cycloid is given by the equations x equals r times theta minus sine of theta, and y is equals r 1 minus cosine of theta, and of course theta has been moving between 0 and 2 pi r. So now this is represented by this particular arc that we see here. This is one of the arcs of the cycloid that we see. Of course, this cycloid is going to have repetitions later, but we're only caring about this simple arc. So let's actually go and use the surface area formula in this. So we're going to have our formulas here, and let's copy the equation of the cycloid. We're going to have number 1, x is equals r theta minus sine of theta, and y equals r 1 minus cos of theta, and we have that this is between 0 and 2 pi r. Then of course, if we set up the area for this is going to be the integral for 0 to 2 pi r of y dx. This is what the normal area is going to be, but translating this to the actual curve, this is only going to be 0 to 2 pi over here, and then we have g of t, which is the function that we have for g. So it's going to be r1 minus cosine of theta, and then we're going to have f prime of t, which is the derivative of this, or in this case, of course, is going to be f prime of theta, because theta is our parameter here. And so this is going to be, again, we're going to have another r here, and the derivative of this, the derivative of theta is 1, and the derivative of sine is cosine, so we have 1 minus cosine of theta again, and then this is going to be d theta, since that's the parameter. Now this means that this is overall r squared 0 to 2 pi 1 minus cosine of theta squared d theta. Of course, to integrate this, we break this apart. This is a binomial square, so this is 1 minus twice cosine of theta plus cosine square of theta. For the most part, this is an easy integration, except for maybe the cosine square of theta, which needs to be transformed. And so we're going to do just that. This is r squared 0 to pi. And then this is 1 minus 2 cosine of theta plus 1/2 of 1 plus cosine of 2 theta. Okay. At this point, we can integrate. And so this is r square, and this is going to be this is just going to be here theta minus 2 sine of theta plus and then if we integrate this here, this is going to be 1/2 theta plus 1/4 sine of 2 theta. And this is going to be, of course, between 0 and 2 pi. So we simplify this out. This is going to be r squared times, we plug in 2 pi, a lot of these things are going to go away. This 1/2 of theta plus theta is going to be 3/2 of theta, but in 2 pi, this is going to be 3/2 of 2 pi, which is going to be the surviving term because sine of 2 pi is 0, and sine of 2 theta with 2 pi is 0, and plugging 0 and all the others, it produces the same. So this at the end is going to be 3 pi r squared. And this is going to be the area here, which is going to be in terms of r. And which kind of makes sense because we don't know what r is. So depending on what r is, then that's going to be our area. Now let's go for using the same, but now instead of doing area, we're going to find arc length. And notice that now we're going to have a little bit of a difference. Theta is going to go between 0 and 2 pi. So let's go for number 2. We have here arc length for x equals r theta minus sine of theta, and y equals r1 minus cos of theta, and we have theta moving between 0 and 2 pi. So now again, our parameter is theta, and we're gonna be using the formula for arc length, which is gonna be in terms of the interval that we're going, and we have the derivatives for each of the parts of the curve. So moving on to this piece. Then we can find out first what is where's going to be the derivative in each of these cases. So first, notice that we have that x prime is r1 minus cosine of theta, and of course y prime is going to be r1 and cosine, the derivative is minus sine, so this is going to be plus sine of theta. And so now we want to put this into play with what we got. So that's going to be the integral from 0 to 2 pi. And in this case, of course, notice that this is dx d theta square plus the y d theta square, or I'm changing the order here, and this is going to be d theta, and so that means 0 to 2 pi, and the r square is going to be on both of these terms, so I can kind of factor that out. And wait a minute, I have a mistake in here. So this is 1 minus cosine of theta, so this 1 is going to go away. This is just going to be sine of theta there. So this is going to be r squared 1 minus cosine of theta plus r squared sine square of theta. And then you can break apart this difference here, this binomial square. We can factor out now the r square, and this is 1 minus 2 cosine of theta plus cosine square of theta, and then plus sine square of theta. You can see that we have the main trigonometric identity here with cosine square plus sine square of theta, so this is going to become 1. And so at the end, this is just going to be L equals 0 to 2 pi of the square root of r squared is going to be r. And now here we're going to be left with 2 minus 2 cosine of theta. This is just going to be what is left in there. Now at this point, we obviously integrate what this is. We can use factoring also here, as we did before. We can use the fact that sine square of theta is just 1 minus cosine of 2 theta over 2. And then if we consider this as, or let me just change the variable. Let me just change this to be x. So now I can say that 2x is equals theta, right? So I can use this in here. I can change all this to be the square root of 2r integral from 0 to 2 pi. And then now I'm changing this to be, wait a minute, I don't need to put out the square root of 2. I'm just going to leave it there. I'm just going to put this as square root of 2, 1 minus cos of theta. And so in that way, I can just transform this to square root of 4 sine square of theta half. And now I can take a square root both of this, and this is 0 to 2 pi, 2 sine of theta half, the theta. Now I can integrate by substitution in here by doing u equals theta over 2. And so this, and don't forget, let's not forget the r. The r is still here. And so this is going to be, when I integrate, this is going to be 2r with minus 2 cosine of theta over 2 from 0 to 2 pi. And then at this point, I just plug in the values. Cosine and pi is minus 1. So I'm actually going to have that this is 2r times 2 plus 2. Notice that cosine in here is also 1. So I get to have, because in pi, cosine of pi is minus 1, this shifts the value here. And then the minus with the minus becomes a plus, and it gives me another 2. So this is going to be 8r. Okay? And so that is the example for arc length. So as you can see, it's a lot of the same things that we've been doing in the normal calculus, and especially in the first part when we were doing integration and we were doing arc length, and we also were doing surface area and area. And talking about surface area, now the third example is going to be to show that the surface area of the sphere is actually 4 pi r squared. And so we're going to use the formula for what is rotating a semicircle, and we're going to find out that this is 4 pi r squared. So let me go back here and so see. Let's say show that surface area of the sphere is 4 pi r squared. And so for this, we're going to take a semicircle. We're going to take x equals r cosine of t, and we're going to do x equals r sine of t. Notice that if you have like a semicircle, and this here t is going to be from 0 to pi. And so what this is doing is simply taking this piece of a circle of radius r, and what we're going to do is, of course, we're going to rotate this. And so when we rotate this around, we're going to have a sphere. Okay, so we're going to rotate this semicircle around the x-axis. And so by using the formula from the surface area that we have here in the top, notice it's very similar to the one for the r length. It's 2 pi y and then the square root. So alpha beta and 2 pi y, and then we have the square root of y prime square plus x prime square, and then whatever the parameters here, we're going to use dt here. So because we need x prime, this is going to be minus r sine of t, and y is going to be r cosine of t, y prime. And then of course we check the values. Alpha and beta is going to be 0 and pi, and this is going to be 2 pi, and then we're putting y, which is sine of t, r sine of t, sorry, r sine of t here. We're replacing this value here, r sine of t, and then the square root y prime, we plug r cosine. Wait, I'm doing things backwards. This should be, no, I'm right. X prime should be r minus r sine of t in square plus r cosine of t in square, and dt here. And so now this is 0 to 2 pi, 0 to 2 pi of 2 pi r sine of t, and then we can check the integral result. As you can see, we're going to get sine square plus cosine square times r square, and so that's just going to leave me with square root of r square. So simply I can go with integral 0 to pi of 2 pi r square sine of t dt. So we're just simply integrating sine at the end of the day, because 2 pi and r squared, none of this is going to be part of the integral, and this is just the integral from 0 to pi of sine of t dt. And once that we set this up, we're pretty much done. This is 2 pi r squared, and the integral of sine is minus cosine between 0 and pi. And again, cosine of minus pi is minus 1. With a minus, it becomes another plus. So this is just going to give me a 2, and this is going to become 4 pi r squared. So as you can see, the calculations are very straightforward. You're just simply taking the pieces of the curve and plugging in each of these formulas. You just need to know how to arrange the formulas in the right way once that you have the curve. So that's all for this section.